Okay. Assalamu alaikum. My name is Anam, and today my topic of presentation is metal organic based piezoelectric sensor. What will be its chemistry and how we can utilize these sensors in the biomedical device manufacturing. Okay, before discussing the whole topic, I will introduce you the basic points of these topics, just like as a story. Can you imagine how, if the energy generated by your heartbeat could help power the very devices used to monitor your health? Or can you imagine how you ever wondered how your body's movement can power the devices you wear every day? Okay, to put it into a nutshell, just like as a story, just set your imagination. Imagine being able to wear a device that tracks your health continuously without needing to charge it. This is actually the power of piezoelectric materials in the wearable technology. Okay, today we will explore how the integration of the piezoelectric materials in the medical devices is revolutionizing health monitoring, offering both the energy efficiency as well as reliability. Did you know that nearly 30% of the patients undergoing spinal fusion surgeries can now benefit from the continuous real-time monitoring through the innovative sensor technology, which are mostly basically their chemistry lies within the MOF-based piezoelectric sensor. As the topic of my discussion mostly related to the two terms, what will be the piezoelectric sensors and what is the MOF, which is the abbreviation of the metal organic framework. Before going towards its detailed description, I will discuss first of all what the terms piezoelectric sensors and what the term metal organic framework indicates. First of all, imagine the concept of the piezoelectric sensor. What will be the application or on which rules piezoelectric sensor works? Piezoelectric sensors are the devices that convert the mechanical pressure or the vibrations into the electrical signals using the piezoelectric effect. This effect occurs when the certain materials known as piezoelectrics, which may be a quartz, ceramics, or certain polymers, generate an electrical charge when subjected to the stress or the deformation. In a piezoelectric sensors, when the force or the pressure is applied, the piezoelectric material undergoes a mechanical deformations which leads to the generation of an electrical charge. This charge is then measured and converted into an electrical signal which can be used to monitor the various physical parameters like force, pressure, acceleration, even vibrations. If you talk about the applications, what will be the applications in our daily life by utilizing the piezoelectric sensors? We can also make wearable devices, we can utilize in the medical devices, industrial machinery, consumer electronics. Mostly in the whole presentation, I will discuss about the wearable devices which are utilized in your medical field. What does wearable devices term indicate? For example, for detecting the body movements or the vibration. Mostly in the medical devices, you will monitor the heartbeats or the muscle activity. That's whole topic related to the terms that is piezoelectric sensor. And the second terms that is metal organic framework. In the short form, we can represent it by the MOF. MOF, actually metal organic framework, MOFs are a class of the porous crystalline material composed of the metal ions at the clusters coordinated to the organic molecules, which may be a ligand, forming a highly ordered three-dimensional network. These materials combine the structural features of the both metals and organic compounds. Because of the two portions of the MOF, that is metal and the organic, they also called as hybrid molecules, and it have various applications in the various fields, but mostly in this whole presentation I will discuss the application of the MOF based piezoelectric sensor in the biomedical device. Okay, let me start our presentation in a brief way. First of all, I will discuss about the abstract of my whole discussion, of my whole research, of my whole topic. What will be concluded in the abstract? I will discuss in the abstract actually Basically, the advancement in the technology have enabled the transformations of the bulky electronics into the compact smart wearable devices. A key focus is harnessing thermal and the mechanical energy from the human activities to power these devices, reducing reliance on the external power sources, which is the basically principle of the piezoelectric sensors. Researchers are exploring the materials that convert the body energy into the electrical power, aiming to create efficient, sustainable solution for the wearable technologies. In these articles, I will highlight the potential of the metal organic frameworks, which are actually the class of the porous crystalline hybrid materials made from the metal as well as the ligand. I will discuss the chemistry of the MOF base containing materials in the next slide. I will discuss it in under the topics of the introduction. Actually, morphs are versatile and widely used across the various fields. For example, if we take an example of the heart rate sensors, basically heart rate sensors generates are imaging the all the waves, all the signals which are creating from the heart in order to detect the various cardiovascular disorders. For example, heart rate sensors has been developed using a composite material of the polyvinylidene fluoride co-trifluoroethylene, which are in the short form represented by the PVDF, TRFE, and the barium strontium titanate (BST) particles, which is mostly related for the detection of the heart rate sensors. Okay, next we will move towards the introduction of the topic. Actually, MOVs possess several distinctive characteristics which make them highly attractive for various applications. And their attractive properties, which are attractive for the various applications, includes high surface area, low density, porosity, excellent thermal stability, high crystallinity, and adaptable optoelectronic and magnetic properties. Such properties are particularly valuable in the development of advanced material for the energy storage, catalysis, as well as in the environmental applications. For example, MOFs have found significant use in the energy technologies, including white light emitting devices. We can also generate the near infrared light emitting devices, where their tunable optical properties are of great importance. Basically, the term MOF came into the widespread in 1955 after the development of the copper-based frameworks. And the first MOF, which was stable and mostly utilized under the humid conditions, was named as MOF 5, whose chemical formula zinc ions is the metal part, and 1,4-dicarbooxybenzene, which is mostly related to the organic ligands. But the problem for the utilization of the MOF5 in the various applications that it is very sensitive to the moisture. So it is challenging how to utilize the beneficial effects of the MOF5. So we are mostly focusing on the advancement in the development of the MOF that are stable in the humid or aqueous environment. In recent years, MOFs have been applied extensively in the range of industries, including energy storage devices, as I discussed earlier, catalysis, biomedical imaging, hydrogen storage, chemical sensing, and hydrocarbon separation. The rapid advancement in the nanotechnology also optimize the properties and functionalities of the MOF, particularly through the nano and the microcrystallization of these materials. What will be the chemistry which is more attractive for the various utilization of the MOF based sensors? As I discussed earlier, metal organic framework basically composed of two parts. One is the metal centers and the second one is the organic ligand. And the third things which coordinate the metal and the organic is definitely the chemical bond, and that chemical bond was named as coordinate covalent bond. Metal, if you talk about the metal centers in the MOF, which is typically a transition metals belonging to the D block elements, which may be a zinc, copper, iron, nickel, cobalt, or the rare earth metals, are the metal clusters. These metals act as a coordination center that link the organic ligand together. Coordination center actually the those part of the coordination compounds which have ability to attract the electron to accept the electron from the ligand. The metal ions generally have a high coordination number, and the geometric coordination number is actually indicate how many ligands attached to the dead central atom. Greater the number of ligands attached to the central metal atom, greater will be its coordination number. And the geometry can influence the final structure of the MOF. The metal anodes are responsible for the catalytic and electronic properties of the MOFs in many applications. Second one is the organic ligand. The organic ligands are usually carboxylates such as terephthalic acid, phosphonates, or other organic molecules with a functional group that can coordinate to the metal center, or in other words, which have ability to donate the pair of electron like oxygen, nitrogen, or sulfur. These ligands are the key to controlling the frameworks of the porosity and functionality. Ligands can be functionalized to impart the specific properties such as hydrophobicity, polarity, or reactivity. The choice of the ligand determines the geometry of the metal ligand bonds and thus overall structure of the MOF. Now we will discuss how the metal centers and the coordinated ligand bonded with each other. It is actually the chemical bond which is named as coordination bond. The chemistry between the metal centers and the organic ligand is typically governed by the coordination bond, where the metal atoms at the cluster forms a bond with the electron rich atom, that is oxygen, either will be oxygen or nitrogen of the organic ligands. These coordination bonds can be covalent or ionic in nature and are responsible for stabilizing the structure of the MOF. So they can be utilized in the various applications. If it is stability, retain. The strength and the nature of these interactions can vary and can affect the MOF stability, porosity, and chemical reactivity. And as it is shown below the diagram, here is the spherical ball represent the metal ions at the clusters and the sprinkling organic linkers, and they coordinated and give rise to the definitely a crystalline structure which are named as metal organic framework, which is a hybrid. Hybrid, why it is called hybrid? Because it is a combination of the metal as well as organic ligands. Okay. Before discussing the applications, how we can utilize the metal organic based piezoelectric sensors in our medical field, further discussion about the metal organic framework or in any other piezoelectric sensors. The growing need for the self-powered flexible piezoelectric sensor is driven by the limitations of the traditional bioanalytical technique. Why we need to develop the piezoelectric sensors? Because of their various limitations and shortcomings which we have been facing in the traditional bioanalytical techniques, which offer problem or they suffer from the issues such as inflexibility and high power consumption. For example, conventional sensors like those used in the wrist pulse monitoring are typically rigid and require substantial energy input, making them less suitable for the continuous long-term utilization. In contrast, self-powered flexible piezoelectric sensors offer significant advantages, including their ability to generate piezoelectric sensors offer significantly advantages. Either it have ability to generate electrical energy from the mechanical stimuli, eliminating the need for the external power sources. This not only enhances the energy efficiency but also enables a seamless integration into the variable devices, facilitating more comfortable and sustainable health monitoring solutions. Because of these benefits, the adoption of the self-powered flexible sensors is becoming increasingly crucial in advancing modern bioanalytical techniques. Current wearable skin sensors, although widely developed, face limitations primarily related to their sensitivity to the environmental factors such as air and moisture. These challenges significantly impact their prolonged usability and performance. Additionally, achieving the consistent adhesion and tight adherence to the skin remains a persistent issue, affecting the reliability and comfort of the long term wear. As a result, enhancing the durability and skin compatibility of these sensors is crucial for their effective application in the continuous health monitoring. Addressing these issues is essential for improving the overall performance and user experience of the skin integrated wearable technologies. In this perspective, we utilize either the piezoelectric materials, triboelectric material, and piezoresistive material. Okay. Okay, now we will discuss about its application in the various field like in the healthcare. Mostly, my topic of the presentation is mostly related to its application in the medical field. If you talk about its application, there are various application, but the basically how to apply these MOF based piezoelectric sensors in the medical field is basically follow a mechanism. That mechanism was named as host guest interaction. After the interaction of the target biomarkers specific to the specific diseases with a more porous framework as a result of physical properties of sensor changes such as electrical conductivity, fluorescence, or the mass that enable them to accurate and real-time detection. How we can utilize this host gas interactions and or what will be the mechanism? Actually, the porous structure of the morph act as a host for the specific biomolecules at the target biomarkers associated with particular diseases. Upon interaction with these biomarkers, morph framework undergoes structural as well as electronic changes that lead to the detectable alternation in the sensor's physical properties. And all those changes may include the shifts in the electrical conductivity, either your electrical conductivity changes, fluorescence changes, mass changes, all of which are key indicators for the accurate real-time detection of the target disease-related biomarkers. If you talk about the application in the various biomedical diseases for the detection of early detection of the diseases and to treat it, in particularly, morph-based sensors have gained attention in the early detection of the diabetes, primarily for their ability to monitor the blood glucose level with a high sensitivity and selectivity. Why were we preferring the morph over the traditional method for measuring the detection of the diabetes? Because of their high sensitivity and selectivity for the detection of the glucose level in your blood in the early stages. Morph consists, as it is discussed earlier, morph consisting of the metal ions at the clusters coordinated to the organic ligands offer a unique combination of the tunable structural properties, high surface area, porous architecture, making them ideal candidates for sensing the applications. These materials exhibit excellent versatility, allowing for the functionalization with a specific molecule to the target and bind a wide range of the analytes, including glucose. By incorporating glucose binding molecules on the morph surface, researchers have demonstrated the potential how to detect even a slight changes in the glucose concentration, offering a novel method for the non-invasive monitoring of the blood glucose level. Basically the major target of the morph utilization sensors is the non-invasive monitoring of the blood glucose level. It's free from the any sort of the pain. The strategy behind the morph-based glucose sensors lies in the precise modification of the morph surface with glucose recognition units such as glucose binding proteins, synthetic receptors or enzyme, which are able to detect how much the glucose level rise or fall in the body susceptible to the glucose detection. Upon glucose binding, these functionalized morph undergo structural or electronic changes which can be transduced into the measurable signals typically in the form of optical, electrochemical and impedance responses. This mechanism enables the sensors to detect glucose variation at the very early stages of the metabolic changes as critical factor in managing diabetes and preventing the complications. Now we will discuss why we prefer the morph-based glucose sensors over the previous method for the detection of the glucose level in your body. One of the most significant features is their non-invasive nature of the morph-based glucose sensors. Traditional blood glucose monitoring methods such as finger prick test are often uncomfortable and can be a barrier to frequent monitoring. Morph-based sensors, however, can be designed to operate through alternative sampling methods such as sweat, saliva, or interstitial fluids, thus providing a more comfortable and user-friendly approach for the continuous glucose monitoring. In contrast, sweat-based, in comparison to all these methodology, we can also utilize the sweat-based technology, which is more comfortable and more user-friendly, offer a promising alternative as the glucose level in the sweat reflect the blood glucose concentration in the real-time monitoring. However, existing sweat-based sensors face challenges regarding sensitivity and stability and long-term usability. Metal organic frameworks have emerged a highly promising material for the electrochemical sensing due to their large surface area, tunable properties, and excellent catalytic activity. The incorporation of the biometallic morphs in the electrochemical sensors have the potential to enhance the selectivity as well as sensitivity required for the glucose detection. Addressing the limitations of the conventional sensors, there's various limitations we are facing in the traditional blood glucose monitoring method. There will be not have any selectivity or sensitivity, and it is not comfortable and not user friendly. But by utilizing the morph based glucose sensors that are more comfortable, more sensitive, more selective for the required glucose detection, as well as they are user friendly. Okay. Next, we will discuss the applications of the MOF-based piezoelectric sensors in the spinal fusion surgery. What will this term indicate spinal fusion surgery? If you talk about the spinal fusion surgery is often used for the conditions like degenerative disc diseases, of trauma and tumors, affecting around 30% of the patient. Traditional methods like CT scans and the X-rays assesses fusion progress, but recent advancement use implantable piezoelectric sensors. These sensors basically convert the mechanical strain which occur in your body into the electrical charges which are stored for the analysis, enabling continuous monitoring of the lumbar fusion healing. Spinal fixation devices equipped with various sensors track the changes in the elastic modulus of the fused area. As the fusion progresses, the modulus increases, reducing the strain on the devices. This system provides real-time insight into the fusion progress by introducing the materials with the increasing elastic moduli between the synthetic vertebrae. That's all about the topic, that is the spinal fusion surgery. If we find its more application in various fields like in the heart rate analysis in order to detect either the cardiovascular diseases ratio all over the world, we can also use the MOF based piezoelectric sensors for the various heart rate analysis. If we talk about the heart rate analysis application of the MOF based piezoelectric sensors, that is mostly related to the generation of the imaging of the materials or the sensing or the vibes which are creating from your unique hearts can be detected with the help of the piezoelectric materials. Basic purpose of the piezoelectric materials in all those devices will be the same. That is the basic principle, is to convert the mechanical stress, mechanical changes into the electrical response that can be measurable, monitorable and detectable. This characteristics arises from the asymmetric arrangement of the electric dipoles within the crystalline structure of the material. Okay, and within the crystalline structure of the material, when these materials undergoes light mechanical strain, whether through compression, tension, or bending, an imbalance in the charge distribution occurs. Okay, and in the cardiovascular sensing, they detect subtle changes in the pressure, vibration, or deformation caused by the blood flow or the heartbeats. These materials are the ideal for the passive sensing application as they can generate. Passive indicates that there will be no requirement of an external power source. They can generate an electrical signal without the aid of the external power source. This energy harvested from the physiological deformations powers the sensors, offering the energy independence and longevity. Key term for the long-term health monitoring. This makes the piezoelectric materials highly suitable for the wearable and implantable devices in the cardiovascular devices. We can also use the piezoelectric materials as well as piezoresistive materials as well as triboelectric materials. If we talk about, we discuss whole about the piezoelectric materials, but if we talk about the triboelectric materials which are based on the triboelectric effect, is another category of the materials being explored for the cardiovascular sensing. Actually, the triboelectric effect occurs when the two materials come into contact and they separate. First of all, they come in contact with each other and then align themselves just like as a separation, leading to the transfer of the charge between them. This phenomenon can be harnessed to generate the electricity or to sense the mechanical stimuli. When applied to the cardiovascular monitoring, triboelectric sensors can detect the minute mechanical motion such as pulse or the blood flow by utilizing the frictional contact between the materials that occurs during the deformations. Triboelectric materials offer the significant advantage of high energy conversion efficiency, even from the low frequency mechanical vibration, which is particularly advantageous in the wearable health monitoring devices. Much like piezoelectric sensors, triboelectric materials can operate passively, harvesting the energy from the body movements without relying on the external power supply. It is also a passive movement. Furthermore, the flexibility and scalability of the triboelectric materials make them ideal for the integration into the flexible and stretchable sensor system, which are increasingly used in the development of the smart textiles and bio-integrated devices for continuous cardiovascular health monitoring. That's all about the triboelectric. If we talk about the piezo-resistive material, which unlike piezoelectric and triboelectric material operate by detecting the changes in their electrical resistance in response to the mechanical deformation. How much resistance will be created by either a stress, either a pressure, either a vibration. When a piezoresistive material is subjected to the strain, its internal resistance varies, and this change can be measured as a variation in the voltage or the current. This property makes a piezoresistive material particularly suitable for the sensors that creates precise and real-time measurement of the pressure, strain, or displacement. In cardiovascular application, piezoresistive sensors can be used to monitor the pressure changes within the blood vessels, measure the heart rate, or detect the changes in the mechanical properties of the heart and arteries. Okay. Now we will discuss about the breathable pressure sensors. We can also utilize the application of MOF-based piezoelectric sensors in the breathable pressure sensors. Actually, heart rate analysis, we can also utilize the piezoelectric sensors. We can also utilize the triboelectric sensors. We can also use the piezoresistive sensors. All these follow the same applications. Their major target is to create electrical signals that can be measurable, detectable, and monitorable. Okay, how we can utilize the MOF-based sensors in the breathable pressure sensors? Cardiovascular diseases account for 31% of the global mortality and more recently have emerged as a leading cause of the confirmed fatalities in the Italy and the China during the COVID-19 pandemic. The global health landscape has been a significant surge in the demand for the accurate at-home diagnostic tools capable of measuring vital signs such as blood pressure, BP, temperature, and respiratory rate. This increased demand has been largely driven by the need for the efficient health monitoring solutions, particularly in the light of the COVID-19 considerable benefits. Home-based diagnostic tools, when integrated with telemedicine capabilities, offer more beneficial. These devices not only facilitate the assessment of the patient's health status, but also support critical functions such as triaging patients to the appropriate level of the care, aiding in the determination of the potential diagnosis, and predicting recovery trajectories. Furthermore, such tools play a pivotal role in enabling real time medical monitoring, particularly for the individuals in the home, ensuring timely interventions and reducing the burden on the healthcare system. This shift towards the remote health care solutions highlight the increasing reliance on the technology to maintain the public health and enhance the patient outcomes. The sensor is designed to offer what will be the benefits of utilizing all these sensors. What will be its response time, recovery times? If we talk about its breathability, how we can beneficial, how we can get benefits? The sensor is designed to offer the fast response and recovery times. With the response time of 22 meter second and recovery time of 20 meter second, these rapid times are particularly significant in the wearable sensors that need to provide real-time feedback for the continuous health monitoring. The fast response ensures that any physiological changes such as variation in the breath rate or the pressure due to the physical activity are detected almost instantly at the spot. Similarly, the fast recovery time guarantees that sensor return to its baseline quickly after detecting a change in the pressure, ensuring continuous monitoring without delay or loss of data. Unlike traditional sensors that may be uncomfortable or restrictive when worn for a long period, this wearable breathable pressure sensor is specifically designed with the breathability in mind. The sensor's ability to allow air and the moisture to pass through it enhances the overall comfort for the user. This feature is especially critical in the wearable applications where prolonged contact with the skin could lead to the discomfort or even skin irritation. By incorporating breathability, the sensor ensures that it can be worn over extended periods without compromising comfort or causing issues related to the moisture buildup, making it ideal for continuous biomonitoring applications. An important consideration for any wearable device is its durability and long-term functionality. The sensors demonstrates exceptional repeatability, maintaining high performance over 15,000 cycles of use. Okay, to put it into a nutshell, as I concluded the whole summary of this my presentation into a few lines. In summary, the newly designed wearable breathable pressure sensors based on the metal organic frameworks represents a significant advancement in the field of the wearable health technology. With its broad sensing range and high sensitivity, rapid response, recovery times, breathability, impressive durability, it offers a comprehensive solution for the continuous and non-invasive biomonitoring. The sensor's ability to maintain high performance over the extended period of the time enables them, combines them with its wireless functionality, position is a key component in the future of personalized healthcare and remote monitoring system. This breakthrough in the sensor technology holds the potential to transform the way we monitor and manage the health, enabling real-time, reliable, and long-time tracking of the vital physiological parameters. Recent advancements in the wearable sensors technology have led to the development of highly efficient, breathable, and flexible pressure sensors. These sensors are essential for the continuous health monitoring, where both comfort and precision will not be compromised. One such non-innovative sensors can be created by sandwiching interconnected nanocomposites of the carbonized metal organic framework and polyaniline nanofibers on the polyurethane sponge, resulting in the composite structures. This new sensor's design offer a highly porous, breathable, and elastic material capable of monitoring both small human activities as well as large human motions with the high sensitivity and reliability. MOF-based materials play a very important role in shaping sustainable technologies, improving the environment outcomes, and advancing the healthcare solutions. In the future, research will likely to focus on rectifying the sustainability, stability, durability, and economic feasibility of the MOF-based material. The development of the flexible and the wearable sensors has revolutionized the landscape of the health monitoring and self-diagnosis. Materials such as piezoelectric, piezoresistive, and triboelectric and capacitive sensors are at the forefront of this transformation, offering numerous advantages that make them ideal for the continuous health monitoring applications. These sensors are lightweight as well as easy to use and can be seamlessly integrated into the wearable devices, making them accessible for both consumers as well as clinical applications. Additionally, their cost effectiveness contributes to their widespread adoption, particularly in the personal healthcare devices. Despite their promising potential, challenges related to the sensitivity, stability, durability, operational range, and biocompatibility of these sensors still persist. Efforts are being made to overcome these limitations to ensure that the sensors can function optimally in the diverse environment, including real-time physiological monitoring. To enhance the performance and broaden the application of these sensors, ongoing research is focused on the development of the novel materials and composites, as well as improvements in the sensor designs and the fabrication techniques. That's all about my topic. Okay, thank you so much. Allah Hafiz.